Hello, welcome to the wonderful world of physics. This is the beginning of chapter 26 in Physics 104b. We're going to start our look at magnetism. And in this first video, I'm going to cover the first three sections of the chapter. What is magnetism, magnetic force and field, and charged particles in magnetic fields. Let's start with section 1. What is magnetism? If you take a bar magnet and you hang it from a string, just let it float or hang loosely, or if you have a magnetic needle, a magnetized needle, and let it float in a liquid, it will naturally turn to face north. Now, just like with electricity, where we learned that like charges repel and opposite charges attract, we find that in magnetism, we have two poles. So instead of positive and negative charges, we have poles that we call north and south. And that wording comes from the directions on the planet of north and south. And we see that the closer the distance to a magnet, the stronger the force. Now remember, when we talked about electric dipoles, let's say we have a negative and a positive electric charge, how the electric field vectors pointed in the way that you see here. Remember, they always pointed towards negative. So the electric field vectors point in the direction that a positive charge would go, that it would be forced. Well, very similarly, we have magnetic dipoles. And we're going to replace the negative and positive charges with a north and south pole. So here we have a bar magnet. There's a field inside the magnet, but I've not drawn that. I've just drawn on the outside, and you can see the similarity there. The magnetic field vectors, and notice we don't say the M field, we call it the B field. The magnetic field points in the direction that a free-floating north pole of a magnet would point. And that's what a compass is. A compass, the little needle of a compass, is actually just a north-south pole magnet. And usually what we have colored red on a compass, it's the North Pole. And it points towards the south. So if we have it up here where my marker is, it would point to the left. If we have it right here where my marker is, it would point down and to the right. So here you have a animation of a compass. You move it along that magnetic field, and the red, which is the north pole of the compass needle, it just automatically points towards the south pole. So field lines always point from north to south, and the lines show the direction a compass would point. A difference between electric charges and magnetic poles is that electric charges can be isolated. In the previous picture, one of the previous pictures, I showed you a dipole with a positive and negative charge, but you can remove them from each other and just have a positive charge, like a proton. However, magnetic poles cannot be isolated. If you take a magnet, such as you see on the right, and you break it in half, it will just become two magnets. And if you break those in half, you'll just have four magnets, each with a north and south pole. So magnetic monopoles do not exist in nature. Now, we think about magnets. Where did the concept of magnetism come from, at least by human discovery, and where does the word magnet come from? In ancient times, there were rocks that were discovered in Asia Minor. This is near where Turkey is today, and the region was called Magnesia. So these special rocks that were found in Magnesia were, you can see how the word developed. They were called magnets, and they were said to be magnetic. They attracted each other, and they also attracted iron, it was discovered. Well, later on, as languages developed in English, it was called lodestone, although in more modern terminology, in geology, chemistry, we call it magnetite. So what they had discovered was Fe3O4 magnetite. By the 12th century, it was discovered that these magnets, these magnetic rocks, always had a tendency to turn and point north, so they could be used for navigation. That was the advent of the compass. So one pole, one side, always points north. Here is the Earth's magnetic field. So the Earth can be thought of as one big bar magnet, and there's the magnetic field right there. I want you to see, first of all, remember the compass, that a compass needle always points north. So if you think about where my marker is right there, if we had a compass, the needle points north. But remember, opposites attract. So the upshot of it is it's kind of like Benjamin Franklin getting wrong what's positive and negative charges. They, with a 50-50 chance, kind of messed up on this one also. They designated that the pole of a magnet that points north, they figured, well, that's the North Pole because it points north. Then later it was found that opposite poles attract, so it's really the South Pole that would be attracted to a North Pole. Well, the way they got around this is what they decided was it really doesn't matter what you call north and south. They're all labels anyway, as long as they're consistent. So the Earth's north, what we call the direction north, that is actually a magnetic south pole because the compass needle, which is a north pole, points towards it. And so what we call the direction of south, that's actually the Earth's magnetic south pole. And so you can just keep that in mind. That's why even though opposites attract, we have the North Pole of a compass that points north, well, because it's really south. However, to avoid such confusion in most everyday life and navigation, we still call it the Earth's magnetic North Pole. So with that little bit, just keeping that in the back of our minds, we do call it Earth's magnetic North Pole, even though it truly is a South Pole. You have Earth's magnetic North Pole, Earth's magnetic South Pole. I also want you to see that those are not geographic North and South Pole. There's a little bit of a difference, and this changes actually from year to year. When we say geographic North Pole and geographic South Pole, that's actually the axis of rotation of the Earth. And they're somewhat closely aligned with the magnetic pole, but not exactly. In fact, the magnetic pole floats around and it moves a few miles every year, and it's somewhere towards the magnetic North Pole. And as I wrote on the bottom, it moves at about 10 kilometers per year, just kind of floating around. So in navigation, we have to distinguish between true north and magnetic north. So when reading a map, you look at the top of the map, what we call 90 degrees north latitude, that's true north, otherwise known as geographic north. But if you're using a compass to navigate around, your compass points towards magnetic north. That can lead to some problems if your compass is leading you to a different place where you think you're going on the map. So when doing navigation, we have what's called a declination angle, which is on a good navigation map, it shows how much you have to adjust. So if you're pointing your compass at, maybe you need to go at, doesn't matter what direction, let's just say a direction, an azimuth of 32 degrees. Well, if you point your compass at 32 degrees, that's not going to be 32 degrees on the map. There has to be an adjustment. So a good navigation map has some declination angle on the legend, and it shows you how much you have to adjust. And so this map down here just shows generally how much you have to adjust, how much you have to add or subtract to go between magnetic north, what your compass is showing you, and true north. So it says along this line 10 degrees, 12 degrees, etc., either adding or subtracting. Many animals use magnetism for navigation. So birds and bees and bacteria. Here you have on the upper left a bacterium. You can see the scale, 250 nanometers, that actually has magnetite in it. And it's not just one freak example. This is an entire species, and there are many species that have magnetite built into them, and they use that for navigation. Bees and birds also, not all species, I'm not sure how much this is spread through the animal kingdom, but honeybees and some birds also use magnetism. They have a sense of magnetism, which is weird for us because we as humans don't have that, but they have a magnetic sense that helps guide them along the Earth's magnetic field. So to answer the question, what is magnetism? Two important concepts that will develop in the next two chapters. One is that the source of magnetism is moving electric charges. When an electric charge moves, it causes magnetism. So for example, in the Earth is a magnet. It's got a liquid core. It's got these charged particles that are moving, and magnetism comes from that. The other point to keep in mind is that moving electric charges respond to magnetic fields. Not just electric charges. An electric charge sitting still doesn't respond to a magnetic field, but if it's moving, it responds to a magnetic field. So where we're going with this chapter is that moving electric charges both cause magnetism and they also respond to magnetism. Now you think about a bar magnet, and you might be wondering, well, what does that have to do with moving electric charges? There's not a current going through it, but we'll get to that. As we go into section 2, you're going to want to have your hands free for this. We're going to get a little kinetic, play with our hands a bit, because we're going to be using our hands to model and to see which way different vectors are pointing. If a charge, and we'll give it a charge Q, whether it's positive or negative, if it moves in a magnetic field, that's a B vector, it experiences a force F, which is perpendicular to both the magnetic field and the velocity. The equation that governs this is right here. The force, and I give it F sub B, so the force from the magnetic field on a charge is equal to the cross product of QV times B. So it's a cross product vector, vector multiplication. The magnitude of that vector, you can see here to the right of my marker, that the force from the magnetic field is the absolute value of Q times velocity times the magnetic field times the sine of theta. You look at my picture to the right, the way we think, what is theta? Well, line up, we draw those vectors tail to tail. And so you can see a velocity vector of a positive charge. You can see the magnetic field vector. Theta is the angle between those. Now, I'm going to teach you 3 different methods for determining the direction of the force. Magnitude of the force is easy. It's just this equation right here, QVB times sine theta. But for the direction of the force, first of all, remember, it's always going to be perpendicular to both velocity and magnitude. So if after you go through these methods, when you're doing a problem, an example, you should check, is the force that I've drawn, is it actually perpendicular to both V and B? Now, you look at this example right here, and it shows the velocity going up, so the charge particle is moving up. Magnetic field is to the right. And if we just guess which way is the force going, and we think, well, it has to be perpendicular to both of those, we actually have a 50-50 guess. We could say it might be moving out of the page, or it might be pushing into the page. It's actually pushing into the page. And I'm going to show you these 3 methods. Here I have method number 1, and it's a right-hand rule. I don't call it the right-hand rule. I say a right-hand rule because you're going to learn several right-hand rules. And this way is to curl V into B. And by curling V into B, you look here, you see velocity vector and B. So what you're going to do is take your right hand, and most of us are right-handed, so you have to remember, put your pen down and you need to use your right hand for this. And what you're going to do is take your fingers and imagine them curling in the direction from V towards B. And if your thumb is pointing out perpendicularly from your hand, it's pointing in the direction of force. Now you can try that with the example that I've drawn up here. And if you take your hand and curl V into B, you should find your thumb pointing into the page. Now, if you're not getting that, that's okay. I'm going to show you an example. All right, let's take this example right here. I've written the B sideways. I hope you can see that this is in green, a B vector, magnetic field vector. I've just drawn that sideways. And here's a charged particle with velocity V. And I want to take you through, I'm going to show you pictures of me doing this, curling my fingers from V into B. So first of all, you need your right hand. Now there's the same picture. And I'm curling, my fingers go from V into B, and my thumb points out of the page towards the camera. And so there I've drawn the force. It's coming out of the page. Let's do another example. And I'm going to teach you the second right-hand rule. So for the second right-hand rule, again, for a positive charge, you do this. You take your straight hand, meaning your wrist is straight, your fingers are straight, it's all straight, and you point them in the direction of V. And then you're just going to bend your fingers so that they point in the direction of B. And if they don't bend that way, rotate your arms so that they do. And your thumb will point in the direction of F. So let me show you an example. You see this picture, V is going up and to the left, and you can see how I have my straight hand with straight fingers, and the magnetic field with those dots and circles is coming out of the page. So I'm going to rotate my hand so that my fingers can point in the direction of the magnetic field. And there I've rotated my hand, so my arm is still pointing in the direction of V, but my fingers now can bend and point up out of the page. And when I do that, my thumb naturally points as I oppose it perpendicularly away from my hand. My thumb points in the direction of the force. And so there it is. Now, by the way, you can also use the first right-hand rule that I taught you and see that it works here as well. You can try the two different right-hand rules right now on this example. So the first way you can do it is take your right hand and just simply curl from V into B, and your thumb should point in a direction. If you're doing this with your right hand, your thumb should point into the page. The other method, take your outstretched hand with straight fingers, make it all point upward in the direction of V, rotate your arm in such a way that your fingers can bend in the direction of B, and your thumb should once again point into the page. There's a third method that's more mathematical. So those first two methods are best for when you just have a picture. When you have the actual quantities, this way is easier. So it's the matrix method to find F. Remember that F is QV cross B. And here is down below how you can do a cross product with a matrix. It's the determinant of the matrix. And here you have the force vector is Q, and I've just put that off to the side. What I'm really focusing on with this matrix is V cross B. In the first row, make the unit vectors, I hat, j hat, k hat. In the second row, make V vector. And in the third row, make the B vector. Now let's look at the picture that's at the top of the page. The velocity vector, I'm making, as we usually do, x in the right direction, y is up, and z is straight out of the page. So this vector goes straight up in the y direction. It is 0, v, 0. The magnetic field goes straight in the positive x direction. So its magnitude is b, so we say it's b, 0, 0. Then you take the determinant of that 3 by 3 matrix. So to do the determinant, we'll take I hat times, and then we eliminate the row and the column that I hat are in, and we just have this 2 by 2 matrix that is V0, 0, 0. And you take the determinant of that 2 by 2 matrix. So it's V times 0 minus 0 times 0. And that all zeroes out. Next, you subtract J hat times the determinant of the 2 by 2 matrix that you get when you eliminate the row and column that J hat are in. So it's going to be this 0 and this 0 and this B and this 0. So 0 times 0 minus 0 times B, and all that zeroes out. Finally, you say plus K hat. You eliminate K hat's row and column, and you've got this 2 by 2 matrix. The 0, V, B, 0. So let's do that determinant. 0 times 0 minus V times B. So we've got negative V times B. The I hat and the J hat component have gone to 0, and what we're left with is negative, oh, don't forget the Q that's there on the side being multiplied by all this, so negative QVB times K. And so we think, well, the magnitude, that is QVB times the sine of the angle between them. The angle is 90 degrees, so QVB makes sense for the magnitude. The negative in the K hat means it's in the negative Z direction, so into the page. And hopefully doing the two right-hand rules both gave you that result as well. Here's the summary for the 3 rules for finding the direction of force from a charged particle, a positive particle, moving through a magnetic field. The first 2 rules go together, and they're more appropriate for if you're just looking at a picture. And you can use either of those rules. I recommend using them both to make sure you get the same answer. Rule number 3 is more appropriate if you don't have a picture, or if it's very difficult to draw a picture, particularly if velocity and magnetic field go in 3 directions, or 3 dimensions, X, Y, and Z. Sometimes it's hard to draw a picture. Let's do some examples here. And looking down at these 2 at the bottom of the page, you might want to pause the video and figure it out for yourself, but in a few seconds I'm going to say what the answers are. So using your right hand, remember one way is to curl your fingers from V into B. And another way is to have your outstretched arm and point your fingers in the direction of B. But no matter which way you do it, you should get the force pointing up and to the left. So up and to the left. For the second one, that X means that the vector is pointing into the page. And depending on the right-hand rules, or not depending, but with either right-hand rule, you should get the force pointing downward. Let's use the matrix method. And we have here the velocity, and this is from the previous picture. The velocity was going up and to the right. Now we don't know the magnitude, it's so many meters per second, but we can at least get a feel for the direction. So we can normalize the numbers and just say, since it's going at a 45-degree angle, that's about a 1-to-1 ratio in X and Y. So I'm just going to treat those as 1 and 1 in whatever units that's in, 1 and 1. And the magnetic field, let's also give that a magnitude of 1. So here I'm more focusing on what the direction is than the actual, what the magnitude's going to be. So the velocity goes in a direction of 1 in the X direction, 1 in the Y direction. Magnetic field is into the page, so that's -1. And when you take the determinant, it's going to be Q times, and you do the determinant, and perhaps you want to take some time on paper to solve this for yourself. But you should get in the I direction -1. Minus in the J direction. -1 minus 0. And in the k direction, 0 minus 0. So when you put all those together, it becomes -qi plus qj, which means in the negative x direction and the positive y direction. So there's our force going up and to the left, and also that's what the right-hand rule confirms. For the second example, we can use the matrix method. The second line is V, and V is into the page. That's the -z direction, so 0, 0, -1. The magnetic field is in the x direction, so let's just call that 1, 0, 0. And then when you take the determinant in the I hat direction, 0 minus 0, in the j hat direction, it's minus j hat times 0 minus -1, which is a +1. And then the k hat direction, 0 minus 0. So in the end, we get F is -q times j. And again, that assumes the velocity component is 1 and the magnetic field is 1. But it shows you that it's in the negative j hat direction, which means -y downward. Let's think about the magnitude of force. Magnitude of a cross product is the first vector's magnitude times the second vector's magnitude times the sine of the angle. So F equals QVB sine theta. That's going to be maximized when theta is 90 degrees. So here you have a picture to the left. When the charged particle is moving perpendicular to the magnetic field, that's when it's going to feel the most force. But as we decrease that angle, and here we go to the other extreme, my picture on the right, we decrease that angle and bring the sine theta lower, meaning making it a 0-degree angle or a 180-degree angle, then you're going to get no force at all. So when a charged particle is moving with magnetic field or against magnetic field, it feels absolutely no force. It has to cut across magnetic field lines for it to be feeling any force. Let's play with some examples here with the right-hand rule. So I'm going to give you some time. Maybe you want to take some time, pause the video, and play with these and see what answers you come up with. So I welcome you maybe to pause the video right now. Okay, now let's give these answers. For the first one, when you do the right-hand rule, you should get force pointing up and to the right. And we're going to check to make sure that it is indeed perpendicular to both of those. For the next one, with the magnetic field lines coming out of the page, you should get the force going up and to the left. And for the one at the bottom, you should get the force going into the page, your thumb pointing into the page. Let's look at a problem in the back of chapter 26. This is number 42. It says a particle carrying a 50 microcoulomb charge moves with velocity 5i hat plus 3.2 k hat meters per second through a magnetic field 9.4 I hat plus 6.7 j hat Tesla. Find the magnetic force on the particle, form the dot products, FV and FB, to show explicitly that the force is perpendicular to both V and B. All right, well, something I haven't introduced to you yet is how do we quantify magnetic field? And here it comes up in this problem, Tesla, named after Nikola Tesla. That is the unit of magnetism, of magnetic field. Well, here I've written out the given information. There's Q, 50 microcoulombs. V is, be careful of I hat, J hat, and K hat, so it's 5, and then 0, and then 3.2. And then the magnetic field is 9.4 and 6.7 and 0 Teslas. Those are all MKS units. So what is the force? Well, the force vector is QV cross B. So we're going to use the matrix method. So we list out just all the components here, I hat, J hat, K hat, the XYZ components of V, and the XYZ component of B. Then we take the determinant of that matrix, and it's going to be I hat. And here I haven't taken care of the zeros, although I've written them in purple right there. But just in general, it's going to be I hat times VYBZ minus VZBY minus J hat times VXBZ minus VZBX. And you can see I've written all this to the right. Plus K hat VXBY minus VYBX. And now we can plug in all those values as I've done here. Here's our I hat, our J hat, and our K hat component. And so here, as I've multiplied through that vector, I've still got Q on the outside, and the units are meters, Teslas per second. When I multiply through the charges, it becomes this: negative 1072, 1504, and 1675, and all of that is micronewtons. So off to the side, I've written times 10 to the negative 6. So it's all of these micronewtons. That's the force. The second question says to do the dot product and to show explicitly that these are perpendicular, that these vectors are perpendicular to each other. So I'm doing FV right here, and I leave FB for you to do if you want to, but let's just do FV. So the dot product of two vectors, remember, is going to be their x components multiplied plus their y components multiplied plus their z components multiplied. When you do all that, and here we have fx times vx, both of them are, since vy is 0, that zeroes out. And as you go through, do the calculations on your own, you should see that they come to 0. Now, if the dot product is equal to 0, remember what dot product is. It also is FV times the cosine theta. That means if it comes out to 0, that they are perpendicular, because theta must be 90 degrees. Now, all of this in my description has been about a positive charge. For a negative charge, such as electron, it's a really quick adjustment. Use the left-hand rule. So everything I taught you about the right-hand rule for a positive charge, if you're dealing with a negative charge, just use your left hand. The way it's often taught in physics classes is use the right-hand rule, but just know that force goes in the opposite direction. And that works also. Find the direction a positive charge would go, and just know that a negative would go opposite that. But I found the left-hand rule actually to be more useful, because there can be situations where you are given the force and you're given velocity, and you need to, from that, work backwards and find the direction of magnetic field. And it's just harder to apply the rule that says use your right-hand rule and know that electron goes in the opposite direction. It's just much easier to use the left-hand rule. But I encourage you to use both methods. For a negative charge, use the left-hand rule, and also use the right-hand rule and make force go in the opposite direction and see that you do get the same result. But be practiced with both of them. The unit, as I said before, is the Tesla. Now in CGS units, centimeters, grams, seconds, the magnetic field is measured in Gauss, and you might come across in some engineering applications Gauss instead of Tesla. And just so you know, a Gauss is 10 to the negative 4 Teslas. We can do dimensional analysis. If F equals QVB times sine theta, then B, we can solve for that, is F over QV sine theta. Of course, sine theta doesn't have any units, but we can analyze the units and see then that a Tesla is a Newton divided by coulombs divided by meters per second. When we consolidate those nicely, we get that a Tesla dimensionally is equivalent to a Newton second over Coulomb meters. Just to give you some ideas of how much is a Tesla, the Earth's magnetic field at its surface is about 50 microteslas. We have a very strong magnet in the physics classroom, and it is about 1 Tesla. So it's much, much stronger than the Earth's magnetic field. It can definitely overwhelm any compass that's in the vicinity. And a neutron star, which is a very quickly rotating dead core of a star. This is something that it's the size of a city like Los Angeles, and it's spinning sometimes hundreds of times per second. It has a very large magnetic field, typically about 10 to the 7th or 10 to the 8th Teslas. If you look at this picture, here we have a uniform magnetic field, and you can set that up by having a north pole of one magnet and a south pole of another magnet. And remember that magnetic field lines point in the direction that a north pole would point. So it would point away, it would be repelled by the north on the left, it would be attracted to the south on the right. So we have a uniform magnetic field. And hopefully that reminds you of a parallel plate capacitor. With electricity, that's how we set up a uniform electric field. Well, this is a uniform magnetic field. Now imagine we shoot into the page an electron and a proton. So on the left, we've got an electron, we're shooting it into the page. So there, the X next to it is actually the vector going into the page. And you use your right-hand rule, and now is a good time to practice this using your right hand. So I'm pointing my fingers as I talk into the page. That's the direction of velocity. My arm is rotated such that my fingers can bend to the right. And since I'm using my left hand, because that's a negative charge, I'm using my left hand, my thumb points up. Or I could also be using my right hand and my thumb points down. And then I remember that it's an electron, it's negative, so it'll get forced in the opposite direction, meaning up. Now on the right is a proton. We're shooting it into the page, so I'm taking my right hand, velocity goes into the page, and my fingers bend to the right and my thumb points downward. So if you take a negative particle and a positively charged particle and shoot them in the same direction, the electron, the negative particle is going to curl upward, the positive particle is going to curl downwards. And this is how when they discover new elementary particles, subatomic particles, they run them through a magnetic field and they can see what direction it goes, and that gives them a sense of its charge. Let's think about this. A proton moving perpendicular to a uniform magnetic field. And take a minute to use the right-hand rule and convince yourself that it does indeed get forced downwards. So it's going to start to get forced downwards, it's going to curl downwards, but then it's pointing in a different direction. And what we get is something like this, circular motion. So we can actually get a charged particle moving in a circle if we shoot it perpendicular to a magnetic field. Now, the radius of that circle is going to be determined by the force. And remember, the force is determined by how fast it's going and the strength of the magnetic field and the charge. So here's an example. We can calculate these. Let's say that the proton is moving at 2 times 10 to the 7th meters per second in a plane perpendicular to a 0.1 Tesla field. What is the radius of its path? Two equations come to mind. The first is F equals QVB sine theta. Since it's moving perpendicular to the magnetic field, sine theta goes to 1 and force equals QVB. Then there is Newton's law, Newton's second law, F equals ma. And remember, for circular motion, acceleration is v squared over r. So by Newton's second law, the force is mv squared over r. We're going to relate these two. QVB equals mv squared over r. And when we solve for r, we have mv over qb. Now we can plug in all those values. We have the mass of a proton, the speed, the charge of a proton, and the magnetic field, and we get the radius of its path of 2.08 meters. Now what if this were an electron? Well, the first thing, the electron would go in the opposite direction, and we would still, the math works out the same, R equals mv over qb. So we plug in those values. We have the mass of an electron, the charge of an electron, and it's 1.1 millimeters. So what a difference. The proton has a wide radius of more than 2 meters. The electron has a very tiny radius of only 1 millimeter. The difference between them is that the mass, the proton has much more of a mass. It's more resistant to being accelerated, to being pulled around in a circle. And in fact, the ratio of those radii is 1830, and that is the ratio of the masses of those two particles. Let's look at an application of this. It's called a mass spectrometer. The mass spectrometer is an instrument used for separating and identifying atoms and molecules by mass. It relies on magnetic forces on charged particles, and we'll see how it does that. There are two parts of a mass spectrometer, and on this page I've drawn the first part. The first part is simply a velocity selector. And we'll see when we get to the second part why we need this first part. We've got ions that are produced by heating. And these ions are put into, so ions are positively charged atoms. And they're put into this combination electric and magnetic field. Notice that the electric field is pointing up. The magnetic field is pointing out of the page. And how do they produce the electric field going up? Well, remember the parallel plates, positive down here, negative up there. So we have this uniform electric field. Now, when a positive ion gets introduced into there, it's going fast from left to right. It's forced upward by the electric field, but if you use your new right-hand rule, it's forced downward by the magnetic field. It will go straight only if there's a perfect balance between the electric field and the magnetic field. And I'll get to the math on that on the next page. So when they are produced, when the ions are produced by heating, you have ions of many random speeds. The purpose of this velocity selector is that only the ones that are going to pass through this window are going to be going at a certain speed. So some will go up, some will go down, but only ones of a certain speed will go right through this window. All right, so the ones that will go straight are the ones that have a balance between the electric force up and the magnetic force down. So QE, that's the force on the charge in an electric field, equals QVB. Well, Q divides out, and we're left with E equals VB, which means the speed of the ions that go straight, they don't bend upwards, they don't bend downwards, is E over B. And that's why it's called a velocity selector, because the person operating this machine, which was first developed in the year 1919, can select the strength of the electric field, can select the strength of the magnetic field, and get whatever velocity he or she wants. All right, let's go to the second part of the mass spectrometer. Now that we've got, having passed through the window, ions that are all going at the same speed, and it's a known speed because it was selected by E over B. As they pass through the second magnetic field, and I've labeled it B prime, so we don't confuse it with B, the first magnetic field, so B prime, and you can use your right-hand rule to see that this works out. That if you have your right hand going to the right and then fingers point out of the page, thumb points down, and we've got this circular motion. And it moves in a circle, and it's going to hit a photographic plate, and it's going to make a mark, an impression on that photographic plate. Now, what they can do is measure wherever it hit on the photographic plate, they can measure the diameter of the circle, and of course that's going to be twice the radius. The purpose of this machine is to figure out the mass of an ion. So let's see what happens. F equals ma becomes qvb prime equals mv squared over r. This is like what we did a little bit ago in this video where we just solved for radius. Well, now we're solving for the mass. So the mass is q times b prime times r divided by velocity. And remember, the velocity is e over b. So we actually don't care what the velocity is. As the operators of this machine, we know it's just e over b. And so what we get is that the mass of the ions that have shot through that window are the charge times b prime times b, the product of the two magnetic fields, times whatever the radius of its path is divided by electric field. Now, when this was originally done, it was a scientist named J.J. Thomson. He used it to find the mass of neon. And he was surprised to find that there were two impressions on the photographic plate. There were two sets of masses that were 10% different from each other. He was expecting only to find one mass for neon. Well, what he then discovered was isotopes, that neon has, one form of it has 20 atomic mass units, the other is 22 atomic mass units. So this led to the discovery of isotopes. Let's do another example. Let's say a mass spectrometer separates singly ionized iodine 127 from iodine 131. The speed is 1850 meters per second. And the second magnetic field, so B prime is 0.2 teslas, what is the diameter of their arcs? And here we can solve for radius. Once again, I take you through the derivation. F equals ma becomes qvb prime equals mv squared over r. So the radius is mv over qb prime. When we plug in the values, we do it first for iodine 127 and second for iodine 131. Plug in those values. So we need the masses. Iodine 127, that means it's 127 times an atomic mass unit, 1.67 times 10 to the negative 27 kilograms. I should have probably done 1.66. I was thinking the mass of a proton, but it'll be close enough. Then we plug all those in and we get 0.0122 meters, but that's the radius. Let's double that. We get 2.449 centimeters. For iodine 131, we do the same thing and we get 2.526 centimeters. So you can see there's just a small fraction of a centimeter difference given these speeds and magnetic fields, but it is a measurable difference between the two isotopes. That is the end of sections 1, 2, and 3 for chapter 26. Have a great day.